So welcome to experiment number 6, and this one is a thermochemical experiment in which we are going to be measuring the amount of heat evolved or consumed, if you like, during a chemical reaction. Specifically, we have mentioned in class, or we will have mentioned by the time we come to this particular lab, the concept of heat evolution, that is exothermic and endothermic reaction. So you have two substances reacting, and as they react, as part of that chemical reaction, thermochemically, heat can either be consumed as a result of that reaction happening, or it can be evolved. Now, in thermochemistry, we measure that amount of heat and then relate it to the number of moles of reactants and products that are undergoing that reaction. So that's precisely what we are going to be doing in today's lab. And first of all, this is going to be an acid-base reaction, basically known as a neutralization reaction. We're going to be doing hydrochloric acid versus sodium hydroxide, and then later on we'll do the ammonium chloride versus sodium hydroxide combination, and then we'll measure the amount of heat that accompanies that particular reaction. Now, the reaction itself is done in what we call a coffee cup calorimeter, which is basically just this styrofoam cup that that are used for your coffee. And the reason why this one is preferred is because it's insulated. There's going to be very little heat transferred or lost during the chemical reaction, and so we are able to measure the amount of heat transfer fairly accurately using this coffee cup because of its insulation properties. And basically, in order to enhance the insulation further, we have a plastic cup that we insert inside the styrofoam cup, and then this is a cork material, again, which further inhibits the transfer of heat to the external environment. Remember, we're talking about the system, which is the reaction where this is taking place, and the surroundings is everything else around it. So the transfer from the system to the surroundings should be minimal, and that is why we use that, we take that precaution to make that to be very much insulating in that kind of way. So basically, the experiment begins with us determining the temperature of the two solutions, the acid, HCl, and the base, independently of one another. Make sure that the two are at the same temperature before we mix them and before the reaction commences. The moment we put the two solutions together, we should be ready to begin monitoring the temperature change immediately, the moment the two come together in the coffee cup. And so therefore, I'm going to enlist your help. I'm going to be stirring away at this, and you will be taking the temperatures when I say, after every 30 seconds intervals. I'll be timing it, and then I'll be asking you to go ahead and record that temperature as we go. So you will be helping me with this experiment in as far as recording the values, and then we'll see what we've got. The calculations, I'm going to walk you through that later. Okay, so let's begin this experiment. In this graduated cylinder right here, we have 50 ml of 2 molar sodium hydroxide, which we are going to mix with 50 ml of 2 molar hydrochloric acid present that are put in this other graduated cylinder right here. And so, like I mentioned before, the experiment begins with us determining the temperature of these two solutions independently of one another. They should be as close as possible. So as we can see in this one, that's 23.3 degrees Celsius. The temperature sensor that we are using that I've immersed in the hydrochloric acid is reading 23.2 right now. So I'm going to take it out and blow dry it using a piece of Kim wipe right here. I'm going to wipe it dry and then insert it in the other graduated cylinder so that we can read the temperature. Remember, the other one was 23.2, and that should be close to that. We'll give it a few minutes here to stabilize. So it's now reading 22.8.9. The other one was 23.2. So let's give it a few minutes. I would give it probably about 5 minutes to see whether it comes close to the 23.2 that we had in the other one. Now the instructions tell us that if those two values are significantly different from one another, we can warm up or cool either of the solutions so that we can bring them closer to one another. I doubt it will be necessary in this particular one, but let's see how close it comes. We'll give it a few more minutes. So I put it back in the sodium hydroxide and it's now reading 23.1 after giving it about 5 minutes. So I'll check once more by putting it in the acid and we'll see if it comes close to 23.1. The objective here is to have those two temperatures agree with one another to the point of plus or minus 0.2 degrees. So that was 23.1 already. This was 22.9 or 8. So I would say it's pretty close. We are ready to begin the experiment. I'll take this one to be 22.9 and 23.1. That is plus or minus 0.2 degrees Celsius. So with that, we are now ready to begin this experiment. So the first thing that we do is I'm going to pour the sodium hydroxide in the coffee cup calorimeter, transfer the 50 ml in there, and then we should be ready to begin measuring the temperature change immediately we put the two solutions together or in contact with one another. So what I'm basically doing right now is setting my timer right here so that we can begin collecting that data. So remember, we are going to be taking this time intervals, 30-second intervals. So every 30 seconds, I'm going to prompt you to take a reading the moment we begin the experiment. So I'm going to move this and put the sensor in here. Once more, let me wipe dry the sensor itself before putting it in this container right here like this. Okay, so I'm just going to pour the second solution and immediately I'm going to set the timer and we will begin collection of the data. So here we go. So get ready, go. I'm going to pour that in here, close that, and immediately begin stirring up and down. So go ahead and take the first reading now, and then after every 30 seconds as I'm going to be prompting you to do. So take the first reading, 36.2. That's the first reading. Doesn't seem to be changing much, but 36.2. That's 60 seconds, 36.1. Okay, next reading, that's 36. That's 1.5 minutes. Okay, that's 2 minutes, still at 35.9. fluctuating between 35.9 and 36. So we'll take 35.9. It's kind of stabilizing now. Coming closer to 2.5 minutes. Now 35.9 still. Three minutes, 35.8. Coming closer to 3.3 minutes. Take the reading now, 35.7 for 3.3 minutes. 3 minutes, 30 seconds, that is. Coming close to 4 minutes now. That's 4 minutes, 35.7 still, fluctuating between 7 and 6. We'll take 35.6. Four and a half minutes, 35.6 still. We'll take one more reading and that will be it. That's it, 35.5. That's the final reading right there. Okay, so that's the first experiment between sodium hydroxide and HCl. Now we'll go and do the ammonium chloride sodium hydroxide experiment next. So I've decided to repeat the experiment again with a second set of 2 molar sodium hydroxide versus 2 molar hydrochloric acid, just to compare the data between the two experiments. And right now what's going on here is that we have the initial temperature, which is kind of stabilized at 23 degrees Celsius. This is before we begin the experiment, so I'll just move this one and put it in the other solution so that we see whether we have an agreement at 23 degrees Celsius, how close will it come. This one is a little cooler, but I would say it's within the 22.8 thereabout. It's plus or minus 0.2 degrees Celsius. So I think we are good to go. We'll go ahead and begin the experiment. So I'm going to go ahead and insert this probe in here, in the solution, in the coffee cup calorimeter, and then at the same time I'm going to pour this and begin stirring. So let's begin right now. I've started the timer, pour the solution in there, and then begin stirring. So its first reading was 31.0, and now it's going higher. It's 35.5. We'll take the first reading at 30 seconds. That's the first 30 seconds, 35.7, 35.7 at 30 seconds. 1 minute, 35.6. It's 1 minute. One and a half minutes, 35.5. Two minutes, 35.4. Two and a half minutes, 35.5.3. 35.3, 2.5 minutes. Three minutes, 35.2. Three and a half minutes, 35.2. Four minutes, 35.1. So that should be enough data for that experiment. So I have checked the initial temperature, and as you can see, it reads 22.8 degrees, and I've checked it for both solutions. They agree with one another within 0.2 degrees Celsius. So I'm good to go. We're ready to begin the experiment. Now this one is between ammonia and HCl. Ammonia is a base. Hydrochloric acid is your acid, of course, and they are both at the 2 molar concentration. So here we go. So we repeat the experiment now with these two solutions. I'm going to go ahead and begin the timer right here, and then I'm going to pour the solution into the coffee cup calorimeter, and we'll begin timing immediately. The two solutions come into contact with one another. So here we go. Lift this, pour the solution in there, and immediately begin timing. Take the initial temperature, 29.9, and then every 30 seconds after that. That's 30 seconds, 31.4 degrees Celsius. That's 1 minute, 31.3 degrees Celsius. That's 1.5 minutes, 31.2 degrees Celsius. That's 2 minutes, 31.2 degrees Celsius. Two and a half minutes, 31.1 degrees Celsius. That's 3 minutes, 31.1 degrees Celsius. Three and a half minutes, 31 degrees. Four minutes, 31 degrees Celsius. That should be okay to stop the experiment there. So we are good. So the next experiment that we are going to do is the one between the two reagents are going to be sodium hydroxide and ammonium chloride. So the sodium hydroxide is going to be the base here, and the ammonium chloride is going to be the acid. So that's what's coming up next, and that will be the final experiment we do in this section right here. So here comes the final experiment, and this is between the ammonium chloride and sodium hydroxide. So right now in the graduated cylinder we have the ammonium chloride, which is currently at 22.8. I had actually measured the other one, it came to 22.9. So they are within plus or minus 0.2. Actually this one was even closer because it was difference of 0.1 degrees Celsius. So we are now ready to begin the experiment, and I'm going to go ahead and transfer the solution in here, and then we'll begin timing it immediately I mix the two. So here we go. So we'll pour this in here, and immediately we are going to start the timer. 23.4, 0.5, 0.6, 23.7. Let's take that to be the initial temperature, and then we're going to do the collection every 30 seconds as usual. Fast reading 23.8. 1 minute, 23.7. One and a half minutes, 23.7. Two minutes, 23.7. Two and a half minutes, 23.7. As you can see, this one is not changing by much. It's almost stabilized at 23.7 thereabout. Three minutes, 23.7 again. Three and a half minutes, 23.7. One more point and then we'll be done with this. Four minutes, 23.7. So that's not going to change anymore. It's stabilized at 23.7, so we are good. So basically that's the experiment right there. So what we are going to do next, let me put this one here. So what we are going to do next now is to take that data that we have generated and plot a cooling curve or a warming curve. It doesn't really matter which direction it goes. So we are going to estimate the initial and the final temperature. The idea behind this experiment is to get to know how much heat was evolved by estimating the initial temperature. So we have before we began the experiment, we knew what temperature we began with, and at the end of the 4 minutes or so, we have collected all that data. We're going to plot a calibration plot, and then we are going to use that particular amount of temperature that we are going to be obtaining here to calculate the net amount of heat that is evolved or consumed in terms of kilojoules, and then we are going to correlate that with the number of moles of the limiting reactant. Now remember, we are mixing two substances here. We are mixing an acid with a base. We know the molarity of the acid and we also know the molarity of the base. So out of those two, because they are actually at the same concentration, we can take either to be the limiting reactant. So we are going to find out how much is heat is evolved per kilojoule per mole of the limiting reactant that we're going to choose there. So basically that's it. I'm going to walk you through the calculation and then I'm going to have you complete the calculation itself. I'm going to tell you what needs to be done, and then you're going to go ahead and plot do the plots yourselves, and then calculate the amount of heat transferred in this particular process. So I'll see you on the other side.